Welcome to your weekly AI Digest. This is week 34 of 2026. Today we'll cover 3 topics. Let's get started. In today's exploration, we'll delve into an essential aspect of artificial intelligence, AI transparency. Authored by experts in the field, this article underscores the importance of making AI systems understandable and trustworthy. With the rapid adoption of AI in high-stakes contexts, the conversations around governance, explainability, and comprehensive data practices have never been more relevant. Before discussing the key elements of AI transparency, it's vital to understand the landscape of AI deployment. The use of AI has surged across industries like finance, healthcare, and human resources, with its applications often influencing critical decisions. However, many AI systems function as black boxes, leading to a lack of understanding and trust from stakeholders, which is concerning considering the profound impacts these decisions can impose. Prior to the push for transparency, many organizations were slow to document how their AI systems operated, the data they used, and the processes behind their decisions. This previous lack of transparency often resulted in skepticism towards AI-driven solutions. There is a growing realization that informed stakeholders are necessary for trust, acceptance, and effective implementation of AI technologies. The core thesis of the article asserts that AI transparency is crucial for building trust and ensuring ethical use, particularly in high-stakes decisions. By documenting data sources, model behavior, and decision-making processes, organizations can provide meaningful insights to users, regulators, and stakeholders, ultimately averting risks associated with unexamined AI outputs. Supporting this claim, the article highlights that 75% of businesses express concern that a lack of transparency can lead to customer churn. This statistic underscores the commercial importance of establishing clear communication about AI systems to foster trust and engagement among users. Notably, 65% of customer experience leaders identify AI transparency as critical for maintaining trust, emphasizing its strategic role beyond mere compliance. The article also makes clear distinctions between AI transparency, explainability, and interpretability. While transparency encompasses the documentation of data and decisions, explainability seeks to clarify how particular AI outputs are generated. These nuanced definitions are crucial as they inform best practices in AI development and deployment, differentiating foundational documentation from the need for model explanations. Moreover, the article discusses the regulatory landscape, particularly highlighting the EU AI Act. This is the first comprehensive regulatory framework that ties transparency obligations to legal compliance for high-risk AI systems. Article 13 emphasizes the importance of transparency in ensuring users can interpret AI outputs accurately, demonstrating a shift toward more robust governance models in AI. Additionally, the article outlines practical steps for implementing transparency. It states that every model should have a record of its architecture, training data, biases, and any explainability tooling used. By maintaining comprehensive documentation, organizations can prevent disputes related to AI decision-making, ensuring a smoother oversight process and fostering accountability. Looking ahead, the implications of enhanced AI transparency are significant. Businesses that prioritize transparency not only comply with regulatory demands, but also position themselves as trustworthy entities in the eyes of consumers. This proactive approach can lead to a substantial reduction in reputational risks associated with opaque AI operations and biases. In conclusion, AI transparency is not merely a regulatory checkbox, but a foundation for ethical AI governance and stakeholder trust. As regulations evolve and AI technologies become increasingly sophisticated, ongoing commitment to transparency will be vital in effectively managing the risks associated with high-stakes AI applications. In this segment, we explore the insights from an article discussing 2 innovative systems, ACE and ALTK Evolve. These systems enable agents to learn from their own experiences, how they tackle multi-step tasks effectively, and the importance of efficient knowledge delivery. Understanding their distinct approaches provides key insights into token efficiency and overall effectiveness. To grasp the significance of ACE and ALTK Evolve, it's essential to consider the landscape of language model agents. Historically, agents have struggled not due to a lack of knowledge, but rather due to unreliable usage of that knowledge when navigating complex tasks. Previous systems often failed to apply the right API calls or returned inappropriate values, highlighting a critical gap in agent memory and learning capabilities. Both ACE and ALTK Evolve emerged to address these learning shortcomings. They focus on transforming an agent's past experiences into reusable lessons, which can significantly enhance task performance. This transition represents a pivot from traditional methods toward what is labeled agentic memory, marking a noteworthy advancement in the development of intelligent agents. The core claim of the article is that while both ACE and ALTK Evolve enable agents to learn from their experiences, the differing methods of delivering that knowledge have remarkable implications for efficiency, particularly concerning token costs. This caters to the ongoing need for optimization in AI systems, especially as their applications expand across various domains. Both systems utilize what they refer to as lessons. However, the architecture of these lessons differs. ACE compiles an exhaustive playbook for its agents, while ALTK Evolve relies on individually retrievable guidelines. By organizing knowledge differently, each system addresses the same failures but presents distinct user experiences that impact overall utility and token consumption. A crucial factor in performance is how each system measures the effectiveness of their lessons. ACE emphasizes continuous updates and deduplication, thereby ensuring that lessons are assessed and refined as needed. Conversely, ALTK Evolve presents select guidelines based on task requirements, focusing on the context and capacity of the underlying model, which directly influences efficiency and token usage. The implications of these delivery methodologies are starkly illustrated through performance benchmarks in the app world. For instance, ALTK Evolve outperformed ACE on the DeepSeek v3.2 model, with an impressive task goal completion rate of 89.3, roughly 40% less token usage than ACE, which logged 80.4. This showcases how delivery strategy can meaningfully influence both accuracy and resource consumption. Further comparisons indicate that on the GPT-OS 120B model, while ACE led in easy and medium tasks, ALTK Evolve excelled in hard tasks. This reveals a nuanced interaction between task complexity and knowledge delivery, with selective retrieval allowing for more effective learning under challenging conditions, thus reinforcing the importance of tailored guidance. Given these findings, the future of agent-based systems may heavily lean towards retrieval-based delivery methodologies. The shift to prioritizing context-aware retrieval over general instruction following not only enables more efficient token usage, but also enhances the adaptability of agents in complex environments, setting a new standard for AI development. In summary, the evolution of systems like ACE and ALTK Evolve illustrates the critical interplay between knowledge delivery and task efficiency. As the development of agentic memory continues, monitoring the advancements in retrieval methods will be crucial for tracking the next wave of innovations in artificial intelligence and machine learning. An article that explores the intricacies of GPU management practices has unveiled a promising breakthrough in performance. The author delves into how a constraint-aware GPU allocator can dramatically improve utilization rates, emphasizing that utilization, not just intelligence, poses critical challenges in enterprise AI. This shift in focus is crucial for companies harnessing the potential of GPUs in their operations. Before the introduction of this new GPU allocator, the industry primarily relied on FIFO, or first in, first out, scheduling methods. While FIFO is simple and effective under low contention, it falters when multiple workloads, such as training jobs and real-time inference, compete for the same resources. This competition often leads to significant underutilization and wasted capacity. Under FIFO scheduling, real-time inference tasks are served in a strict arrival order, which does not consider workload priority. This can lead to scenarios where high-priority jobs are delayed, significantly impacting overall efficiency and profitability. The GPU resources, often left unutilized during low-demand periods, become a financial burden, decreasing the return on investment for businesses. The core thesis of the article is that switching from FIFO to a constraint-aware GPU allocator can enhance GPU utilization by as much as 33 percentage points. markedly increasing output value. This improvement arises from a sophisticated method that makes allocation decisions based on job priority and demand patterns, rather than simply the order of job arrivals. The article presents several benchmark scenarios to support the claim. In one scenario, GPU utilization rose from 51.6% to 72.4%, demonstrating a notable improvement in how resources were managed. Furthermore, priority-weighted output surged from 7,093 to 10,980, reflecting a 54.8% increase, underscoring the effectiveness of this new allocation method. In a more rigorous testing environment with a training-heavy workload, the allocator achieved an impressive utilization rate of 87.0%, a leap from the previous 53.6%. Additionally, priority-weighted value soared, more than doubling to reach 17,545, illustrating that the allocator not only improves efficiency, but also enhances the overall output quality. Another notable finding is the scale test, where both FIFO and the new allocator demonstrated identical utilization rates of 44.9%. However, the allocator managed to deliver 15.9% more priority-weighted value, emphasizing that effective prioritization can lead to increased value generation, not just capacity filling. The implications of this study are profound for the enterprise AI landscape. Organizations utilizing GPUs can foresee substantial improvements in their resource management strategies. As demand patterns evolve, systems that prioritize allocation decisions based on real-time traffic can avoid significant idle capacity, translating into lower operational costs and higher performance. In conclusion, the introduction of a constraint-aware GPU allocator marks a pivotal moment in the management of enterprise resources. By shifting the focus from simply filling GPU capacity to understanding demand and prioritization, companies can unlock the potential for significant financial benefits. Monitoring developments in this space will be crucial for organizations looking to leverage AI more effectively. In a recent article by Liquid AI, the release of QADQ4_0G-GUFs marks a significant advancement for LFM 2.5 models. This update showcases how developers can now utilize 4-bit checkpoints that enhance both performance and efficiency. As the demand for optimized AI models continues to rise, understanding this development is crucial for those in the tech industry. Prior to this update, deploying large AI language models often required substantial computational resources, limiting their accessibility. The existing models face challenges in balancing performance with memory requirements, causing inefficiencies and potential drop-offs in accuracy. Developers sought solutions that would allow these models to function effectively across a range of hardware configurations. Traditional quantization techniques often resulted in significant drops in model accuracy when transitioning from higher precision formats, such as BF16, to more compact forms like 4-bit. This gap in efficiency led to a demand for new methods that preserve the integrity of model outputs while making the models lighter and faster. The introduction of Quantization-Aware distillation represented an innovative step forward in this respect. The core thesis of the article asserts that QADQ4_0G-GUFs provide updated 4-bit checkpoints for LFM 2.5 models, managing to maintain performance levels comparable to their BF16 counterparts while enhancing memory efficiency and speed. This advancement enables developers to deploy these models on a wide range of hardware without sacrificing quality. Notably, the QAD checkpoints recover an impressive 97% of BF16 average accuracy lost to quantization. This means that even after transitioning to a much smaller model size, the ability to reproduce quality outputs remains remarkably high. This statistic serves as a testament to the effectiveness of quantization-aware distillation as a powerful technique. The reported performance retention rates for various models are equally impressive. The LFM 2.5-230M, LFM 2.5-350M, LFM 2.5 to 1.2B instruct, and LFM 2.5 to 2.6B maintain 97.1%, 96.5%, 97.4%, and 96.6% of their respective BF16 baseline performances. This consistent performance across different model sizes underscores the versatility of the QAD approach. When it comes to practical applications, the speed improvements facilitated by QADQ4_0 checkpoints are striking. The decode throughput for LFM2.5-230M and LFM2.5-350M models show up to a 33% improvement compared to previous benchmarks, ensuring faster processing times without compromising quality. The 1.2B and 2.6B models also show remarkable throughput increases of 3 to 14%, making them well suited for edge deployment. Furthermore, these improvements are not just in isolation. The QADQ4_0 checkpoints outperform external benchmarks, such as Unsloth's UDQ4_K_XL, in relevant contexts. This positions the QAD checkpoints as strong contenders in the landscape of AI quantization techniques, offering a competitive edge crucial for developers aiming for high performance in constrained environments. Looking ahead, the advancements in QADQ4_0 GGUFs could reshape the future of AI model deployment significantly. As more developers adopt these models, we may see a broader trend toward quantization-aware techniques that balance performance and efficiency, reducing barriers for AI applications across various industries, from edge computing to mobile devices. In conclusion, the release of QADQ4_0 GGUFs exemplifies the progress being made in the realm of AI efficiency and performance. As developers explore these advancements, one can expect to see innovative applications in edge technologies, enabling broader access to high-performing AI across different platforms. Today, we're diving deep into the innovations behind LFM 2.5D Spark, a cutting-edge model that promises up to 3.2 times faster inference speeds. This significant enhancement in processing efficiency is not just a technical upgrade. It reflects ongoing advancements in large language models and their applications in various industries. Understanding DSpark's underlying technology, benefits, and potential implications can shed light on its transformative impact. Before the introduction of DSpark models, the field of large language models witnessed a steady increase in performance. However, achieving high throughput while maintaining quality output remained a challenge due to the memory-bound nature of the decoding process. Traditionally, latency arose primarily from data retrieval, often leaving computational efforts underutilized. Innovations in decoding mechanisms, therefore, became crucial for pushing these models toward greater efficiency. One of the most notable concepts leading to this advancement is speculative decoding, which helps streamline the token generation process. In previous models, generating each token in succession often meant sequentially loading weights, a practice that led to unnecessary delays. DSpark's approach rethinks this methodology significantly, focusing on reducing the function calling latency and speeding up the inference process by making efficient use of system resources. The core assertion of the LFM 2.5 DSpark framework is that it can achieve notable improvements in inference speed without sacrificing output quality. Specifically, the new models exhibit a throughput enhancement of up to 3.18 times on GPUs and up to 2.87 times on devices. This leap in performance translates to real-world gains for applications reliant on quick and efficient processing of language tasks. Metrics reveal the impressive capabilities of LFM 2.5 DSpark. For instance, in benchmarks across various datasets, the LFM 2.5 to 2.6B model significantly reduced function calling latency by an average of 57%. This reduction illustrates how well DSpark enhances performance in multi-tool scenarios, making it particularly viable for applications requiring rapid responses. In tests using advanced hardware like the H100 GPU and M4 Max MacBook Pro, benchmarks indicated impressive speedups across the datasets assessed. For instance, the Math 500 dataset showed up to 3.06 times speed improvement on the H100, while on the M4 Max, speeds soared from 61 to 137 tokens per second, nearly doubling throughput. Such results underline the practical implications of implementing DSpark in real-world applications. Analyzing specific tasks provides deeper insights. For example, the human eval dataset saw LFM 2.5 to 2.6b reach 161 tokens per second on the M4 Max from 61 and 835 tokens per second on the H100, highlighting DSpark's capacity to handle challenging programming tasks. These remarkable speeds can enhance developer productivity and elevate user experiences in interactive applications. Moreover, LFM 2.5-8BA1B demonstrates that while acceptance rates are higher than traditional models, on-device speeds are comparatively lower, with only an 18% improvement on average. This serves as an important note. Depending on the model and context, performance gains may vary significantly. Understanding these nuances is critical for users seeking to harness DSpark's capabilities effectively. The implications of implementing LFM 2.5 DSpark are vast. With such improvements in inference speed and efficiency, industries relying on natural language processing, such as automation, customer service, and programming assistance, stand to gain immensely. Predictably, swift and reliable AI-driven interactions will foster further innovation and uptake of AI solutions across varying sectors. As the landscape of large language models continues to evolve, innovations like LFM 2.5 DSpark not only redefine performance standards but also pave the way for future advancements. Observing how developers and organizations adapt to and leverage these technologies will be crucial as AI plays an increasingly central role in our everyday lives.